Okay.
Hi, folks. Welcome to the Monday seminar. Really nice to see you all. Really happy that today Michael Mann is joining us from Nome, Alaska, to talk about some recent stuff that he's been doing with subduction megathrusts and trying to understand the evidence for elevated pore pressure. As you well know, that's one of the ideas that a lot of people have about how slow earthquakes work, about what slows them down, makes them work at all. And there was a formal announcement by email, and if you'd like to join that email list, if you're not on it, then I'll put that information in the chat pretty soon here. But our normal mode of operation will follow again today. It's just simply to ask people to mute at the beginning during the talk. If you have some point of clarification, Michael has already said that he's happy to be interrupted for point of clarification. And then, you know, for real sort of in-depth questions and detailed discussion and stuff, we'll go ahead and have an extended discussion after the talk. So, Michael, thank you very much for joining us, and I'll leave it to you.
Okay. Here, can everybody see my screen?
Looks good.
Okay. Let me start the presentation. Just get this set up correctly.
Yeah, perfect.
Okay. So thanks, Chris. Thanks for inviting me. I'm happy to do this on kind of short notice, but it's fine. Let me get this out of the way. All right. So this slide with a ton of writing and a giant title is, we're going to get this started. So I'm effectively looking at the environment surrounding the subduction megathrust using receiver functions or scattered phases. I'll go over what that means, for all of you non-seismologists and maybe students who don't know about that yet. So we're taking a kind of fresh new look at the high pore fluid pressure hypothesis and a very specific version of it that I'll get into. This is work that I started when I was a PhD student at Cornell, and I continued as a postdoc at Woods Hole, and finally finished and just got recently published last month, maybe a month and a half ago in oh no, not even that long ago, in EPSL. So all these results can be found here. I can, happy to share the paper with anybody who wants to ask. But so we're talking about the plate interface, and the plate interface itself. This is in the subduction zone. This is the region that hosts the Earth's largest earthquakes. It generates the largest tsunami. I mean, it's one of the most important faults or fault zones in the world, and it shows a little bit of variation. So, okay. In this talk, I'm gonna talk a little bit of background on the plate interface itself, the different receiver function methods, sort of more traditional ones, and sorry, just a little distracted. More traditional ones, and then the kind of new-ish. I mean, it's an old method, but a new application of an old method here, and then talk about receiver function imaging in Cascadia, and which is the central west coast of North America, and then receiver function imaging in Alaska, the northwest coast of North America, and then compare the two. And I'll go over the method that we use for inverting the receiver functions for plate interface properties and results and conclusions, and a short discussion. My title gave it away, but a short discussion that kind of discusses some alternative hypotheses to high pore fluid pressure, and what that might mean. So, am I having to click? Okay. So the plate interface, the seismogenic zone, can be kind of divvied up into three different regions. So there's this shallow region. It's less than about 10 to 12 kilometers depth. There's stable sliding. They're slow earthquakes. They're low frequency earthquakes. That transitions at some point right around 10 to 12 kilometers to a locked region. This is kind of the region where megathrust earthquakes nucleate. They start, but they can rupture all the way up dip into the shallow region itself. And then there's this deeper region that I'll call a few different things, but really this is the region of slow transient slip. This is the episodic tremor and slip region, and it's different from this up dip region in that it's deeper down, and the transition from locked to this is a little bit less understood. And what I mean by that is, if we take a look at the shallow region, this is a region that hosts very low frequency earthquakes, slow earthquakes, and stable sliding generally. And sometimes you'll get subducted sediment along the interface. Sometimes it looks like it's scraped off, but in most cases, you'll see uh, this slow, stable sliding, and that's interpreted as being the result of subducted sediment or an interface that has very high pore porosity and very high pore fluid pressure. That's kind of lifting the interface apart. You think of it as like weakening the interface and changing the frictional dynamics along it. But at a certain depth, especially with sediment, diagenesis and lithification of that sedimentary layer that's subducted along the interface just completely dewaters and closes the pores. You can see this in reflectivity images right around 10 kilometers depth. So at shallow depth, there's high pore fluid pressure, very, very shallow depths. There's high pore fluid pressure, but by 10 to 12 kilometers depth, almost all of that is completely gone from the interface between the plates. So that transitions a little bit down dip into uh, sort of the deeper regions. And this is the main thrust of what I'm going to be talking about, this kind of difference between these two regions, what's actually going on and why it changes down dip. So this is just from Japan. You can look at, so this yellow regions are the regions of megathrust earthquakes. And then you go down dip and you start to get in the region of slow slip and tremor. And in this down dip, so in the yellow region we get more normal earthquakes rupturing, but in the down dip region you get series of low frequency earthquakes, and then tremor, which is also thought to be just a superposition of a ton of low frequency earthquakes, kind of chattering along the interface almost constantly. And what causes this change in rupture behavior is sort of the focus here. So we're going to be looking at this down dip region and using receiver functions and kind of examining the properties and, and, and moving from there and inferring what might be going on. So what do I mean by episodic tremor and slip in this down dip region? This is sort of a classic figure at this point, but the chattering of tremor along the interface tends to have these spikes that are correlated with slip along the interface that's not associated with megathrust earthquakes, with these massive earthquakes. Although, if you look at them in their entirety, they tend to add up to pretty significant earthquakes over time. What causes this difference is still unknown. This difference between the megathrust region and this down dip region. If you look at the low frequency earthquakes themselves, that are thought to make up kind of the bulk of tremor, the biggest, most impulsive low frequency earthquakes can be used to generate focal mechanisms. And these focal mechanisms, just to give you a hint, I mean, subduction direction is kind of to the right, to the upper right in these images, but most of the focal mechanisms from these low frequency earthquakes look like shallow thrusting events. So these look like they're earthquakes along some kind of interface between the two plates. Um, and, uh, and yeah, but whether or not that interface occurs at the plate boundary, at the top of some subducted sedimentary column, whether it anastomoses through, some plate interface fault zone, at these depths, it's difficult to tell. Again, this is below 30-ish kilometers depth, 20, 30 kilometers depth at a gigapascal. Well, you can map out where tremor occurs. So this is sort of a map of tremor density across all of Cascadia. This is the boundary between Canada and the United States here, Western North America. And the tremor itself tends to follow the contours of the subducting plate. And it's continuous. It spans almost 1,000 kilometers long strike here. It's dozens of kilometers wide, and it's a band of, this is a pretty robust observation of tremor down dip of the megathrust region. So when we look at this region using other methods, so like geophysical techniques, one thing to point out, I mean, this in the bottom right is a map from northern Cascadia. Not a map, a model of conductivity and color of northern Cascadia. Black dots are earthquakes. These blue circles are low frequency earthquakes, and these kind of lines drawn on here are lines from active source imaging that imply or actually, I think that's conductivity, that imply sort of a highly conductive interface region that suggests the presence of water. And I'll leave it kind of vague like that. It suggests the presence of water, but and interconnected pores. But when you look seismically at this region, so this is in Japan, at a certain position down dip, you'll see a peak in the long-term slow slip region is correlated with a region in the subducting crust of high VPVS. So this is a tomographic model. And when I say high VPVS and when other people say high VPVS, these things actually, there's a lot of strange crosstalk. People in the receiver function community who talk about high VPVS are talking about 2.3, whereas in tomography, they're typically talking about 1.8 to 1.9. And if you look at this range, this whole color bar here, this is roughly the span of all normal rocks that you might find in a subduction zone in the plate interface region. So right at the center of the long-term slow slip region, they see this elevated, region of high VPVS. But high VPVS here, I mean, if you really look closely, peaks at about 1.9. There might be one little spot here that's around 2, but it's still it's pretty low. And actually see if I can do. No, never mind. Nope. It's well low. It's relatively high VPVS ratio, and this observation has been used much like the shallower updip region to imply that this interface is weak here, and that's why it's showing similar dynamics to what you see in the shallow, like upper 10 kilometers of the plate interface. But in these tomography models, regularization, how the models are generated will smooth out sharp variations. So in order to generate a model that has sort of high fidelity to the data, you have to add in this regularization, and that kind of gets rid of anomalous outliers. So you're less likely to recover extremely high VPVS in a small region in a tomographic model. So that's why we use this other technique, receiver function. So here is a receiver function, kind of really interesting way of plotting these receiver functions, but showing the plate interface in blue kind of coming down here. And that's exactly falls on where these low frequency earthquakes are occurring. And then the subducting, oceanic crust moho down below it in red. And I'll get into what receiver functions are next. But basically, they've lined this up and shown that this is occurring within the subducting crust. This top and bottom blue and red feature in the receiver functions down here. This is this low velocity zone where the what I would call the plate interface region, and that's what we're going to be analyzing. So what do I mean by receiver functions? So so receiver functions are essentially waveforms that isolate scattered seismic phases beneath a seismometer. So in my case, I'm going to be using P wave receiver functions. So what happens is you have a distant earthquake, let's say a P wave, and so here's the earthquake. As it travels, that P wave bottoms in the lower mantle. Let's say the source is 2 different pulses, just for this example, and it's arriving underneath this receiver that I've drawn with an inverted triangle here because I didn't pay attention. And let's say the only boundary that exists beneath the receiver, the sharp velocity contrast, is the moho. So when that P wave comes up and interacts with the moho, it generates a converted S wave that follows it to the surface. And that converted S wave, because S waves and P waves are orthogonal roughly, for this case, that S wave will be registered and measured on the horizontal components of the seismometer, and that P wave will mostly be on the vertical. So here's what I mean by that. So that P wave coming up, here's the vertical component, that's the P wave arriving, and then it sort of bounces around a little bit, and that's what these small other wiggles are. But on the radial component, you have that P wave coming in because, again, it's not coming up perfectly vertical. It comes up at an angle, so it's recorded on both components. But then there are these much higher amplitude other phases coming in here, and we're trying to tease out those because those are the P to S scattered phases. So one way we can do that is deconvolve or remove the vertical component from the radial component. And what this does effectively is kind of it removes the source and instrument components of this. So all you're left with is this kind of waveform that represents scattering. So what is this? So in a traditional receiver function, you're going to get a big peak at 0, and that's sort of showing that's the P wave aligning on both components and being deconvolved. So that's what people typically look at to see, that's a sign of like health of a receiver function in this more traditional method. Um, and then here there are 3 other wiggles, we'll call them phases. And they arrive at different times. They have slightly different amplitudes, and what these are is going to be important. So I'm going to take a little bit of time on this slide and really kind of work through this. So this first wiggle is, I call it PXS. As the P wave comes under the MOHO and interacts with the MOHO, it generates an S wave that follows it to the surface. And this time difference between these two phases has to do with the velocities of the crust, and the amplitude here has to do with the magnitude of the velocity contrast across the MOHO. So this is the first phase that comes in. If people are doing more traditional receiver function imaging or analysis, they tend to look for this phase pretty much most of the time. If you're in a continental region, you can expect this phase to arrive right around 4 or 5 seconds. So, that's from the MOHO. So that's here. The second one, that P wave will actually reflect off the surface and backscatter toward P to S waves or S waves towards the surface off that boundary. So that's the second one here. I call this little p X S. So this is the surface. Again, I'm going to be throwing these out quite a bit. So I just want to make sure that I go over this slowly and carefully. And this is this phase is this mode of scattering. Each one of these is a different mode of scattering. Um, this mode is also typically used in analysis, especially in subduction zones. It tends to look very good, but as you get later in the receiver function, again, all 3 of these are superimposed on each other. So it's actually kind of difficult to tell what's coming from one mode at a deeper time or a later mode at a deeper boundary, or a later mode at a shallower boundary. So those can tend to overlap. And then this third mode, PSXS, we're not going to be analyzing, but I'm going to be pointing it out in some photos or some figures. That P wave will come up and reflect off the surface, and when it reflects at an angle, it generates a little converted S wave that bounces and just reflects off of boundaries. So those are the 3 main modes of conversion. In the receiver functions I'm going to be analyzing, I generate them in a slightly different way. So this has been around for a while. They're array-based receiver functions, and the way that this works, it's sort of taking advantage of of an aspect of receiver functions that exists in, let's say, subduction zones or areas, or using an array that spans non-horizontal boundaries. So here's a series of synthetic receiver functions, again, with the same 2-pulse source. The generic, it's not that important what it is. I just wanted to show that it doesn't have to be one. Over a boundary that's dipping. So each one of these you can think of as a seismometer, vertical component of a seismometer, uh, over a dipping boundary, and with increasing depth going up. So you can see the reflections off of that dipping boundary are occurring at a deeper and deeper and deeper, or later and later and later time. But if you take this and you stack all of these together, you just take the average, you can take the principal component, you can do any fancy thing you want, but if you stack all of these the reflections off of that dipping boundary don't appear in the stack. So instead of taking the vertical component, let's say, of one receiver function, or one seismometer, so if I just pick this one in the middle, this vertical component has these other wiggles in it. And when you deconvolve that out of the radial component, those wiggles will disappear. You can't actually recover the P to P reflections off of boundaries using a traditional method. But if you have this array, you can stack it, get a this nice looking incident wave field, which is a better measurement of the incident P wave. And so this is the source. So instead of assuming the vertical component is like the source, we're actually measuring the source or the incident wave field that generates the scattered wave field here. So, and it's worth noting that, yeah, I call this PPXP, and this is the novel approach that we're doing. We're using this phase to analyze the plate interface in a way that nobody's done before. So okay. One other thing that we've done is we sort of tuned these arrays. So we on each station we analyze. So on the left is, I mean, it's not important. I'll go over it in a minute. But on the left is Alaska, and on the right is Cascadia, and I'm comparing these two results. But these are just two different seismometer arrays, and you can tell where there's blue, it's lower velocity, and actually there's a big sedimentary basin here, and here, and up here, and up here. And everywhere else it's a little more normal. Near the coast the velocities are a little lower, but essentially what this is doing is if you have a faster surface velocity, the P wave will come in at a higher angle, and if it's slower it comes in at a more steep angle, or sorry, less steep angle. So what we're doing is tuning the array kind of like a satellite array to aim towards the incident wave field. So this accounts for amplitude variability due to surface velocity differences, and theoretically, this makes a much better measurement of the incident P wave field. So we're using array-based deconvolution, and we've tuned each array to kind of take into account absolutely everything that we can to make the best looking receiver functions. So these array-based receiver functions, this is what they look like, and the power of these will be clear in a second. So the black is just like the more traditional receiver function I was showing before. We remove that peak at 0 because we subtract the incident wave field measured from the stack of the P components. And we're left with the three main phases. They're all clear. They're all exactly the same. Although the amplitude is slightly different. They're all the same, and they show the exact same information. The delay times are the same, and the amplitude ratios are roughly the same. But what we also get is a second waveform, this P component, and that's where we can recover the P to P scattering. And so now, instead of having three different modes to work with a third one that people generally don't analyze that much because it's difficult to, there's a lot of move out at such later times that it's difficult to tell what you're looking at. Instead of only having three modes, we now have four to analyze. And it's this fourth one that's the real key here to analyzing the plate interface region. So just as an example, here's what in Cascadia receiver functions look like. So positive here is shown in gray, and negative is just not filled in. These are different receiver functions shown in dark blue here and plotted roughly west to east, distant from the coast. And what you'll see is a low velocity zone. Now, what I mean by that is a negative receiver function phase over a positive receiver function phase. And so that's here is the top of that low velocity zone. A negative phase here implies it's faster above the interface and slower below the interface. Now, this is actually sort of interesting, just like fundamental observation to note. Faster above the interface when the subducting crust is oceanic and the overriding crust is continental. It is an interesting observation in itself. And then a little bit later, there's a positive conversion, and this is slower above the interface and faster below. So this, excuse me, this negative positive doublet is a hallmark of a low velocity zone. As in, what this implies is that the velocity decreases and then it increases. This is a simplification of exactly what's going on, but it's so here. So we're analyzing these kinds of phases to look at the properties between the two based on their differential travel time. And I'll get into the method in a minute. So just north of that, these are probably the best receiver functions and the best looking stations in all of Cascadia. These are on Vancouver Island. They're right above all of these black dots are tremor. So these stations are deployed directly over this down dip region. And so here are receiver functions. So, okay, so there's a lot of variability, but I can kind of show the general gist of it. As you go to the right, these stations are over an increasingly deeper subducting slab. And if you kind of squint, you can see the top and bottom of the low velocity zone in this first conversion, PXS here. And then another one here. This is PPXS, again, the top and bottom of that plate interface zone. And then here a little bit deeper is PSXS. So all three of these are kind of superimposed, but because the structure is, it's dipping, we're fairly confident we know what we're looking at. These are easy to tease out and figure out what's going on. You can imagine if you just had one of these stations, it would be very difficult to tell what was going on. But because, we have these arrays, now we're able to do more complicated imaging. So when we have dense arrays like this, we can do much more complicated imaging. So with the receiver functions, there's one method. I'm going to be kind of showing a lot of these plots, so it's worth talking about. It's called, we migrate these receiver functions in kind of an analog to what's done in active source studies. So these migrations, if you have a dense enough set of stations, you can do a two-dimensional migration that correctly accounts for the effects of dip, and you're imaging the discontinuities themselves as well as their relative velocity contrast. So you're actually getting out a value here. And so where it disappears is important. It might not be just data based. That might actually be the value, the amplitude of the velocity contrast across the boundary disappearing. This is a kind of a classic paper. But what is this imaging? So you see a red region here. Well, what we're actually imaging is the top and bottom of that red region. So where a receiver function would be negative positive, this negative positive actually corresponds to the white line, like the white areas between colors. So what we're imaging, what is here labeled as basaltic crust, this is this low velocity zone. And yeah. So this is receiver function migration imaging, and then I'm also going to be talking about common conversion point stacking of receiver functions. I'm just going to show results of these, and I'm just going to briefly go over this and summarize it for any of you who don't know. The receiver function migration kind of moves the receiver function to where the conversion point at depth after accounting for dip. But in a more simple approach, we can just project the receiver functions to depth, assuming everything is horizontal. Now, things that are dipping too steeply will kind of get phased out in these images, but it gets out flat-lying boundaries pretty well. You use some velocity model to calculate where these conversions could be coming from, and then you stack them in bins, either in 2 dimensions up here in the top, or in 3 dimensions if you have a 3D array. And you can map out interfaces in over a wide range. So just to show kind of, here's a receiver function migration image, and here's a CCP stacking image using roughly the same data, the same location. You can see the top here is red, and the bottom here the top is blue and the bottom here is red, and that these line up fairly well. Yeah, so when we look at different seismometer arrays deployed across Cascadia, this is in Vancouver Island, so you can think of this as north, central, and southern Cascadia. This low velocity zone booms in all of the images. And what this looks like is about an 8 to 12 kilometer apparent thick low velocity zone, which is clear to about 35 kilometers depth, right about where it reaches the mantle. And then and I know this earlier, but the subducting basaltic crust should be faster than the overriding crust. So there must be something going on at that interface that's causing such a sharp decrease in velocity. The bottom of this low velocity zone is actually, it's an interesting question. I'm going to kind of skip over that for most of this, but for all of you seismologists out there, this is interpreted separately in a lot of different cases. So it's thought to either be the moho of the subducting crust or some mid-crustal boundary And the bottom of it in Cascadia tends to disappear as soon as it kind of reaches the mantle wedge, which is right about the depth of eclogitization of the subducting crust, where the subducting crust would increase in velocity, and that velocity contrast with the mantle and the underlying mantle lithosphere of the subducting plate. Those velocity contrasts would disappear, so the receiver function, which samples velocity contrast, won't get it. So you can see how it's completely non-existent up here. Beneath Mount Rainier in central Washington, the contrast does seem to persist for a little bit deeper, and then also in central Oregon, maybe a little bit deeper. But this low velocity zone is very clear throughout all of Cascadia. And actually, okay, and now getting to the meat and the crux of the comparison here. So previous results, looking at this low velocity zone in Cascadia, using kind of the best data in Vancouver Island, using traditional receiver function method, all these stations are deployed directly over this low velocity zone. You can look at, and I'll get into the weeds of the exact method in a little bit, but you can look at the differential timing of each of these modes and compare them and invert for the properties of the low velocity zone. And when I say properties, I mean you get a thickness estimate and you get a VPVS value. And it's much more robust at getting VPVS. When you look at these signals, you get VPVS ratios that span 1.8 to greater than 3. That's incredibly high. If you take the best version of these measurements, you get something around 2.3, and there's some variability. But these values, again, are higher than all the lithologies that you would expect to find along the plate interface in this region. So what does that mean? Well, in order to create such high VPVS, you need high porosity. You have to reduce VS relative to VP somehow. And the only way to do that is to have a lot of pore space. But this is at a gigapascal. So in order to maintain 2.5 to 4% porosity at a gigapascal, you need very high pore fluid pressure. And that's where this observation comes from. Oh, that slide should be one earlier. But so this is where this high pore fluid pressure hypothesis comes from. So because high VPVS, in my case, high VPVS would be greater than 2.1, 2.2, because that's not seen in any subduction zone rocks at these depths, at these PT conditions. You require high porosity and high pore fluid pressure to maintain it down in this episodic tremor and slip region. Because porosity and pore fluids reduce VS more than VP, that fits the VPVS values. Some conductivity measurements up sort of above the plate interface, but also along the plate interface, suggest interconnected pores or the presence of water. And one interesting thing to note, though, is that this hypothesis requires that these highly porous regions that are 4 to 5 kilometers thick, that span 1,000 kilometers north to south and dozens of kilometers wide, don't drain over kind of yearly timescales. And if they do drain, they're immediately, refilled. And so, take that as you will. And then the refilling of this water comes from the constant metamorphism and dehydration of the subducting plate, which I think is still also up for debate how hydrated subducting plates are, especially in Cascadia, which is sort of an end member, warm, hot, subduction zone. So I'm going to be testing this hypothesis with kind of a new method, and I'm comparing Alaska and Cascadia. And the reason I'm doing that is because in Cascadia, the subducting crust is 5 to 7 kilometers thick. This is more normal. You'll find that almost everywhere around the world. But in Alaska, or at least the region of Alaska I'm looking at, the subducting crust is an oceanic plateau, and it's 11 to 30 kilometers thick. It actually varies. It's like a wedge shape. It's like a wedge shape. So this different thickness in crust allows kind of, we can examine the impact that having the moho phase beneath a low velocity zone in Cascadia, because they're right next to each other, or in Alaska, that plate interface is very separate. It's significantly separate from these subducting crusts. And this is shown by, this is just one station in Alaska and one station in Cascadia. On the left in each is the normal receiver functions, and on the right in each of these cases are the P component receiver functions. So what we're looking at is I kind of marked the phases. In Cascadia, it's simple because there's a low velocity zone. It's just one, one set of doublets in each mode. You can pick these out pretty well. So in PXS, that first conversion, this orange here and this blue here, this is the top and bottom of that low velocity zone. And then a little bit later on, if you kind of squint, this is the top and bottom of the low velocity zone in this mode, PPXS. And then in the P component, you can see the top and bottom of the low velocity zone right here. So that's, I would call that Cascadia 1, Cascadia 2. In Alaska, there's actually 3 different phases. The plate interface exhibits itself as a low velocity zone. I'll show a figure of that. But this third boundary below this low velocity zone is the MOHO. And because it's significantly separate from it, like this is the MOHO down here at 15 seconds in PPXS. So this is the plate interface and then the MOHO down here. So it's significantly separate. So it's actually hard to tell. In this figure in Cascadia, we just see the top and bottom of a low velocity zone. So if this includes the oceanic crust, that's okay. But if it doesn't, if the bottom of this low velocity zone is somehow a mid-crustal conversion, where is the MOHO conversion? Are these superimposed on top of each other? Because there must be a velocity jump at the MOHO. I mean, it's the sharpest contrast across the whole region in all active source studies and all tomography in everything. So, and I'm going to be doing this. So I'm going to be analyzing this in 2 different cases, focusing on using this extra PPXP mode and not using it and just incorporating this direct conversion. So reviewing a little bit of receiver function imaging in Alaska, because the subducting crust is thick at shallow depth, what you actually look at in receiver functions is a thin low velocity zone, and this thin low velocity zone is on the plate interface. Here in this image, down dip, this is the subducting oceanic plateau crust. You can see it over here. It's I want to say it's 12 kilometers thick, maybe 13, but up dip, this MOHO, this is where the MOHO should be, this dashed line, and that the plate interface here is just such a strong conversion. It's kind of blotting out everything else going on. But in Alaska at shallow depths, there's a thin low velocity layer along the plate interface. The low velocity zone, actually, here's the boundary of the 1964 earthquake. You don't need to know exactly where this is, but this is generally the study region in South Central Alaska. I'm using these stations in my analysis when I get to it. Here's the projection line for this inversion, and actually up dip here at the shallowest stations, this low velocity zone still exists. So this low velocity zone doesn't just exist in the down dip slow slip region. This is kind of a recurring slow slip here in green. It's not just in the down dip slow slip region. It's also extending into the 1964 earthquake rupture area. And then, in intermediate depth earthquakes kind of permeate the region, but they don't tend to fall within this low velocity zone. If you look, so that was on these stations to the west. If you look a little to the east, you can look at, this is work that I did as a PhD student. You do receiver function migration using these stations. You can see these circles and dots are earthquakes, and we'll ignore the bottom one. So we'll just interpret the top one. You can see the subducting Yakutat crust here. It's low velocity zone in the mantle, but at shallow depths, we have the MOHO down here. And then the interface itself is this low velocity zone. And actually, what we've done is we did receiver function migration and CCP stacking in 3 dimensions. So we use the migration, which correctly accounts for dip, to find plate interface phases. And then in the 3-dimensional imaging, we follow it all the way along strike from these 2 different migration lines. So this is where this low velocity zone appears. We actually see this in our CCP stacking, the top and bottom, and we've actually mapped it out. It's not that important. So here, across the southern portion of the region, we've mapped out the plate interface. This is this red dot, blue dot here. That's the top and bottom of the low velocity zone along the interface. And then these yellow squares are the MOHO of the subducting crust. So this looks a little blotchy. It's hard to tell what we're looking at. Are we sure that we're actually getting this correctly? Well, we did this in all 4 of the receiver function modes. And I know there's a lot going on here, but just look at the red and blue squares. They're exactly the same on all 4 of these. They're picked from a composite stack of mode, CCP stacking modes here. So if I just plot them on each individual one, you can see that this sorry, we had something in the way. That in PXS, we have the plate interface region as a low velocity zone extending across the whole region. In PPXS, we see this low velocity zone extending across the whole region, this negative positive. SXS even, we see this low velocity zone extending across the whole region at the same depth. In PPXP, we also see this, and this is what kind of triggered the thought to us to use this. We can map this boundary out across the whole region, and we've actually, we've done this, and it spans a wide range. It actually, the area of the low velocity zone, it's ruptured at least twice in the relatively recent past, and so it's not confined to the tremor region. So either high pore fluid pressure influences megathrust earthquake rupture, or this low velocity zone represents something else going on along the interface, and it might not necessarily require high pore fluid pressure. So how are we going to do that? Well, with a receiver function, in a traditional way, the depth to this boundary, like h to something like a continental moho, assuming VS in this case, or VP in this case, I can't remember. You can stack this. This is called HK stacking. This is the most common method for estimating crustal thickness using receiver functions. They're dependent on the VPVS of the crust and the thickness of the crust and some assumed VP. But what we can do is, and that's an example, what we can do is take this sort of well-known standard method and just change the notation a little bit. So instead of looking at the whole time from the top to the bottom of the crust or a boundary, we can actually look at, excuse me, the differential time from the top and bottom of a low velocity zone. So in this case, instead of that, we have this. So here's an example in Alaska. This is red and blue is the top and bottom of the low velocity zone in PXS. This green borders the top and bottom of the low velocity zone in PPXS. And then we have this extra component that shows the top and bottom of the low velocity zone in PPXP. And based on our CCP stacking, our 3-dimensional imaging, these black lines are spanning across here, these black lines are the projected top of the low velocity zone. So you could say that this lines up very well. We're able to identify exactly which of these wiggles is the low velocity zone and what's not. So what we do is extract these phases. We kind of zero out the top and bottom that are oppositely polarized, and we take the autocorrelation of each one of these. So we want to know the time difference between these two phases. So what an autocorrelation will tell us is kind of waveform dependent, but essentially the time difference between the top and bottom of each of these. This way we don't have to focus on any other velocity. We don't have to guess exactly where a depth is. We don't have to model the whole receiver function. We're just looking at the different timing of the P and S waves that travel in that low velocity zone. So we could take half of this because it's symmetric and plot these figures. So this is our data that goes into the inversion. Just like HK stacking for crustal thickness, we do the same thing, but with a low velocity zone. So this is a method that's been done before. However, this component of it, this is the novel aspect. So here are the trade-off curves for PPXP and PPXS. And when you overlap these, you get sort of an uncertainty range best fit that spans 1.9. It reaches about VPVS of 1.9. There's a best fit VPVS here, but there's some variability in the data. And then we're comparing that with a more traditional method using a normal receiver function, using the same method as previous studies, and overlapping doing the same thing just with these different modes, and they get a completely different answer. And in fact, these are very, very, very high VPVS ratios. It's spanning, 3.2 all the way up to, whatever we let it extend to. Um, you know, these two things can't be true. And the limiting factor here appears to be that this direct conversion has lower resolution, and it does have lower resolution. In, just showing it here in this trade-off curve, what we found from this case one inversion using these two modes, this PXS is actually physically incapable of measuring that. Just like it doesn't overlap. So these two measurements are incompatible with one another. But we went through and we did this for all stations. So case one in Alaska and Cascadia, they both span the range of normal subduction zone rocks. And then in case two, the more traditional method, kind of much, much higher VPVS values. And in fact, if you just kind of like collapse these onto a histogram, the higher values in Cascadia, we've actually recreated the previous values with a peak around 2.4, 2.5, and a little bit more variability. What's important to note, though, is that if if PXS is biased, meaning if the two phases are actually closer together, but there isn't enough frequency content in the waveforms, they look farther apart. So it actually increases this differential timing in PXS. And in case two, that biases the numerator here up and the denominator here down, which actually jacks up VPVS artificially. So these measurements might actually be artificially raised. And then another thing to note is that it seems like they're following the PXS trade-off curve for the previous slide. They follow this trade-off curve, which means it's sort of dominating these types of inversions. So the reason we think PXS is to blame for this direct conversion is that it will bias before other receiver function modes. So for a synthetic test, if you just use a VP of 5 kilometers per second, a VPVS of 2, so this is still pretty high, and a thickness of 2 kilometers is the lower bound. At really high frequency, the top and bottom of the low velocity zone here in red and blue, these dashed lines, that's the true arrival time. At high frequency, they can get it out. But when we filter it to, let's say, 0.5 hertz, which is used in most previous studies of this plate interface VPVS, PXS is completely biased, as in it looks wider than it should be. And oh, sorry. And so just to show that here, unless you have higher than about 2 hertz in PXS, you're going to get a bias in this measurement, and because everybody's filtering higher than that, I mean, they wouldn't be capable of measuring a VPVS or a low velocity zone with these properties. So sort of in conclusion, oh good, still a little bit of time. Sort of in conclusion, I mean, our measurements span the range of real rocks. They're below a VPVS of 2. So at these VPVS ratios, water and high porosity are not required. You don't need elevated porosity to reach these values. Entrained metasediment along the interface could be both the geophysical observation or fit both the geophysical observations and the sort of fault mechanics of it, the frictional properties of sort of the material along the plate interface without the need for water. And then for the seismologists out there, it's worth noting the inclusion of PXS biases measurements to high VPVS. It has, lower resolution. And one thing to note is that other observations from receiver functions may be compromised in this way. So differences in plate interface depth due from receiver functions versus active source imaging are definitely going to be different. Receiver functions would show a shallower interface. Overlying crust VPVS would actually be biased down, and that's also seen. The layer thickness and overall receiver function resolution sort of in general might be a little bit limited. And just another note, just to go back to this high VPVS, the VPVS in the highest resolution tomographic images typically only spans 1.8 to 2. And even the highest resolution ones will reach 2 is very, very rare. It's almost always 1.95 at the very, very high end, 1.9. And even there, that's a little high. but noting that VPVS of densely fractured basalt can reach higher values just without water. And then if you go and you grab exhumed megathrust fault gouge rocks or exhumed megathrust rocks, they show predominantly metasedimentary rocks. There are signs of hydrofracturing, but whether or not that water influence spans 1,000 kilometers along strike and a 4 kilometer thick layer that's 20, 30 kilometers wide, whether or not that's, controlling the entire plane interface properties at these subduction zone scales is, I think something to think about. And then when you measure the VPVS on these dry samples, you yield more normal VPVS ratios. They get high, like up to 2.1, but again, that's in dry cases, and it's mostly due to anisotropy. These are heavily sheared layers that are fast in one direction. And then another thing just to point out, I kind of hinted at this. In Alaska, we see a top and bottom of a low velocity zone and then a later phase. In Cascadia, we just see the top and bottom of the low velocity zone. And if you model a thin low velocity zone over oceanic crust and then filter the receiver functions, you get this blue line here, the top and bottom of the low velocity zone. So there may be additional layering in Cascadia that's sort of obfuscating all of these measurements, and you're not getting out a true measurement of the plate interface using this direct conversion. And then I guess, whatever. I'll just talk about this a little bit. So, and we discuss in my paper some alternative hypotheses for kind of what might be going on, and here are just some observations that might lead people in certain interesting directions. That heterogeneous stress states and variability in frictional properties can lead to slow slip. Fault models can create all kinds of behavior just by varying the proportion of velocity strength and in velocity weakening material. Even beneath glaciers and ice streams, the same fault patch can kind of flip between fast and slow slip earthquakes. And field observations of exhumed megathrust show evidence that it might just be. It seems like heterogeneity needs to be more talked about rather than kind of one cause. And you see a VPVS of 1.9 and you assume, oh, there's all this high pore fluid pressure, affecting the interface over these subduction zone scales. So I think that's it. And thank you.
Michael, great talk, really stimulating, a lot of interesting stuff. So thanks very much. Ask people to join me, unmute if you'd like to. Yeah, great. So our normal mode of operation, and I think good mode with Zoom is to use the reaction button on the bottom of your screen to raise your hand. It looks like that, and we'll give Michael a chance to catch his thoughts for just a second, and start into a discussion. And maybe I'll go first and say, so you talk about it makes really clear you don't need these, very uncertain to have these really high VPVS ratios. And what about so if you take an alternative view about lower VPVS and you think of that in terms of, I don't know, shear fabric or heterogeneity, what's the constraint on how thick the zone might be in that case if you don't interpret it in terms of really high VPVS ratio?
Yeah. Well, the nice part about some of these measurements is the thickness is sort of, it falls out of the analysis, but it's dependent on, we assume a VP in doing this, and then we vary VS to what fits the data. So we can change that VP. So this thickness could be a little different, but in Alaska, it's thin. In this one region where we can isolate the plate interface from the MOHA, where we're just looking at those phases, it looks really thin, like a few kilometers. Here's the thickness at the bottom, spanning 1.5 to about 5 kilometers, depending on exactly where you are. Some of these measurements are better than others, so it's sometimes it's difficult to tell. In Cascadia, it looks a little bit thicker. It seems like overall we're getting about oceanic crustal thickness or a little bit thinner than that. But like I was showing before, the interpretation of thickness, especially with all of the stuff that's going on in here, is actually really difficult because if there's layering, if there are velocity gradients in this region, which there definitely are, the oceanic crust should, steadily increase as you get a little bit deeper. It kind of throws off thickness, but I would say sort of thin. For this region, for like Cascadia, where there's normal oceanic crust, it's hard to tell if we're even including the oceanic crust or not. I would guess that these are on the order of a couple kilometers along the plate interface, and then seismically, what we're imaging might also include oceanic crust, but it all gets kind of fuddled in there.
But so the seismic imaging, when you say oceanic crust, because the images you show, I guess it's just, yeah, right here, 44. It's much thicker than just 1 or 2 kilometers, that red region. What should we be
Yeah,
doing?
yeah. Well, so I mean, the previous hypothesis would be this looks thick because the velocity model they use doesn't have a high VPVS region.
I see.
But actually, if you use a normal VPVS region and you actually look at these phases, specifically, which is what I'm doing here, it doesn't need all these velocity models. It doesn't need all these other things above and below this low velocity zone. When you look at the thickness there, you get whatever the range between 2 and 7 kilometers thick.
Yeah. Yeah. Okay.
Yeah.
Thank you, John Vidali. Go ahead.
Yeah, just yeah, a lot of complicated things there. I mean, look, very nice to not need those high velocity, high Poisson's ratios. I guess my question is, can you just put the whole thing in a 3D finite difference model and generate synthetic seismograms and show that your model works and these alternative models don't? Because then we wouldn't have to go through so many steps of processing. And
yeah, the nice part about what we're doing is actually this is probably the simplest method for getting at the properties. The problem with doing a finite, like some kind of a actual like full waveform modeling of this is what frequency content do you use? So in this analysis, what we actually found, what we're, what's kind of been hinted at for a little while is there's a lot of off-axis, local, random, like incoherent scattering in receiver functions above 1 to 2 hertz. That region, the scattering starts to increase from kind of other boundaries that are within the crust, and you can look at this as like in terms of the coherency between the vertical component and the horizontal components. What you end up with is this kind of like, where do you put the frequency boundary? So we would, based on our analysis, because we're looking at a thin layer, we can actually see where the boundaries start to bias. And it looks like above 1 hertz, you're not getting out. But other people think that they can get up to 2 hertz in receiver function. So it would really depend on where you put that boundary about how complicated you can make your model. And it just gets, I don't know, I think with finite element model, it would just get too complicated at a certain point. So people model the receiver functions. They model these completely fully and the high VPVS fits, but it doesn't fit with the P2P observations that we have. And that's really the key that kind of suggests all of those previous models might be assuming something incorrect about frequency content or, velocity gradients or how that affects the different
but you have
receiver function modes.
model. I mean, you're arguing a specific layering and velocities between the layers, and you can just plug that in. It's too expensive to
this
calculate.
is just an average. This is just an average value for VPVS throughout the low velocity zone, and that's the only thing we have to model.
Okay.
But so in that way, ray theory should cover that just fine. But when we, it just has to do with, this is the first case. I mean, obviously we're gonna take a few steps. We're working on kind of analyzing some of the previous results to see if they agree.
Well, right. But when you're arguing the apparent spreading of the boundaries, that's sort of a finite frequency effect. Anyway, it'd be nice to see some modeling, just the whole structure in there and all the reverberations in a full wave sense.
Yeah.
Good point, John. And so as we go to Alex Shubnell, I'd just like to encourage, especially early career people, but everybody, join the conversation. Raise your hand. Alex, go ahead.
Hello, Michael. So thank you so very much for this very interesting talk, because I never realized how much uncertainty there was actually in all these high VPVS measurements coming from receiver functions. And so I have two questions. So the first one is, in your model, so if you show slide 40, just here, it
Yeah.
seems that the best, I mean, the lowest error always is bounded at very, very
Yeah.
low VPVS. In fact, if you were searching for even lower VPVS, you would probably, I mean, it seems from the shape of your error ellipses, it would actually even try to go to even lower VPVS, possibly.
Yeah. Yeah, the reason, so I kind of ignoring that. We're really focusing on the kind of the difference between the case 1 and case 2 inversion suggests there's something wrong. And so we're pointing at kind of this direct conversion as being the culprit, this PXS having lower resolution. However, if the layer is too thin, this is the kind of bias for the higher resolution case. This PPXP will bias before PPXS. So if there's bias in this, it's actually going to get biased down a little bit. And I think I have some synthetic tests. There's also the fact that so you could see synthetic tests for a VPVS of 2 and a certain thickness. I don't remember how thick this was. Because of waveforms interacting and overlapping at different depths to the low velocity zone, because there's a superposition of all these different modes, it gets biased down for all kinds of reasons, even just, let me think, even just these phases interacting with the next set, PS, XS, or something, they can cause different biases. But sort of overall, yeah, I mean, it looks like they're bounded a little bit at the edge. But the uncertainty ranges span the range of real rocks. So yeah, but good eye. I mean, yeah, that's an issue that we're trying to figure out exactly.
Yeah, and so my second question is, so there is a number of people in rock physics nowadays who are working on the frequency dependence of elastic properties, and as a matter of fact, the Poisson ratio is a weird elastic properties in a weird elastic property because it's not a moduli. So the way it evolves with frequency is actually non-trivial.
Okay.
And so would it be possible to do these receiver function, I call them maps, but they are not, or images, at different frequency to see how stable it is? Like, if you go to very, very low frequency, of course you will lose in your spatial resolution, but try to span to make those maps like at 0.1 hertz to 2 hertz, and see how stable the result becomes.
You give me 1 second. I did this analysis at one station at a bunch of different frequencies in my PhD thesis. I have it right here. Let me just, okay. So you mean something like this? So we did a third inversion case in my PhD thesis, but essentially, as you filter it at different low pass frequencies, it remains the same. And then right about 1.5 to 1 hertz, it starts to deviate. And then based on, you could see because PPXS is biased down, that starts to go down. And then because the direct conversion is biased up, that starts to go up.
Mm-hmm.
And that's, sort of, yeah.
Yeah, so yeah, it would be interesting to have to see, but I mean, but exactly.
Actually do an inversion taking that into account rather than just looking. Yeah, definitely.
Thank you very much. Very nice. Thank you.
Yeah, good points. Someone else has a comment or question?
Well, I have another quick question. Is there any, I mean, you showed a little bit of tomography from Japan, but are there other studies that try to be higher resolution? I mean, can you look around the world and find studies that resemble more yours or the other case of the geometry?
The reason I pointed out Oh, do I include that? Yeah. Oh, I didn't have that. Put it down here. Did it? Calvert, Andrew Calvert, did a study in 2020 where he took active source along the exact this Vancouver Island region. You know, they did that in the Bay, and and they really focused on kind of matching up the receiver function imaging with the active source imaging. And in those, I mean, the VPVS maxes out at 1.83 for that region, and they kind of hid that a little bit, but like it's hard to tell exactly what's going on. I know in Japan, I mean, earlier models reach 2, but again, it's it's a VPVS of 2 in like one grid node. It's never that. It's never a huge region of high VPVS. It's always one tiny little dot somewhere. That's again the slope sub region is a wide region, and it's never quite as big as that. But if VPVS is a difficult measurement to make, so I don't know. I haven't looked that carefully. This is more of just an observation that when people talk about high VPVS, it's what do they mean? Do they mean 1.9? Do they mean 1.85? Do they mean 2.3? Like that's.
If I can just comment on this, I completely agree with you.
Okay.
And one of the things, however, that you say in the plot that you just showed before with the VPVS increasing with, or the Poisson ratio increasing with porosity, in fact, and it's something we've tried to argue for a long time. You don't just need porosity, you need crack-like porosity to really, really slow down S wave. I mean, you need to have like inclusions that are actually elongated so that the S wave.
Oh yeah. The aspect ratio really matters. Yeah.
So the shape of the porosity is very important because you won't slow down S wave very much with spherical pores. So in order to have very, very high Poisson ratio or apparent Poisson ratio, you would need like very, very elongated ellipsoidal tracks.
Which you might expect here, but yeah.
Interesting points. Julia, go ahead.
Hi, thank you for a fantastic talk. This is really interesting. I have a general kind of question about this slide, actually, thinking about like heterogeneity, and I'm looking at the left-hand column in the second figure, and I see this big red blob with a labeled subducted ridge. I'm wondering how like a subducted ridge would influence the VPVS ratio.
It's been a while since I read this paper. Does anybody remember exactly? No. So I'm pretty sure they're interpreting this subducted ridge and that there might be something different happening here. And then I think these are faults going through the crust, and I think they're saying that this ridge is sort of interacting with things and creating like fluid pathways for fluid along the interface. But it's been a while. It's been a while.
Okay, that's
I'm sorry.
So then,
I should know this. I'm showing.
I can also just go to the paper and read the paper. And so then how would that kind of affect your model?
Oh, I mean, that would be an anomaly at one spot. Yeah. People say, depending on how high resolution your imaging is, people see subducted ridges everywhere. We know that they probably subduct, but they're usually kilometer scale vertical offsets, and they're very wide, so it's hard to kind of tell exactly where they are. I forgot what this is coming from exactly, but because it's correlated with this higher VPVS region, I'm sure it has something to do with it. I should really know. I apologize.
Sorry. Thank you.
I have another quick question. I mean, I've heard interpretations where there's like 2 layers in the subducted crust. Do you see any signs of something like that?
Yeah, I for the life of me, I've been meaning to talk to some people about that. I know. I mean, sometimes, every once in a while, let me try to find some. Every once in a while, the kind of phases, you'll see a negative positive for the kind of layering of this is not negative positive for the layering of like Cascadian subducting crust. At this, so these are filtered a little bit. So at higher frequencies, you might be able to see that. You can see here, this looks like a negative positive and then maybe a positive below that. So there might be an interface and then a deeper boundary. but I don't know. I don't see any internal boundaries. The low velocity zone is pretty well established, especially at these like lower frequencies, as just a top and bottom of something. And if this doesn't include the oceanic crust, like the moho, then I don't know. Someone's gonna have to explain to me where that moho is below these signals because I've never seen it.
And the
And the
slow
moho's
slope,
got to be the. Oh, sorry.
slow
Go on.
slope events are at the upper boundary of the low velocity zone or across the lower
So
velocity zone?
there's a interesting weird stuff. This is from that paper where he's comparing a bunch of different observations. So these blue circles are above the moho and presumably within the low velocity zone. Um, yeah, they tend to be within it or above it. And the again, I would stress that the uncertainty in receiver function depth is the problem there. And it's because of all these various factors that resulting from bias or velocity gradients that don't capture sort of the frequency content of the receiver function correctly.
Yeah, great. Thanks. Great talk.
Other points? It feels like we could draw in the geologists who want to tell us exactly what these slow slip regions look like. I know lots of people think about that. One of the things you definitely see in regions that look like they could be slow slip or complicated, you see evidence of hydrofracking and quartz veining. So
Yeah.
there's always that. But then from a laboratory point of view, you pointed out, and lots of other people have too, that you can make slow slip happen in the laboratory without high pore pressure. So
I don't know if somebody's asking a question or if that's in the background.
Yeah.
Well, so I mean, I think it's worth pointing out a little bit that the depth of this slow slip tends to be roughly the same, even in subduction zones that are very, very different. So in Alaska, you have subducting oceanic plateau. The depth range is almost exactly the same. Where these kind of slow slip and tremor events are in Cascadia, the depth range is roughly the same, even though it's very, very hot, buoyant, subducting crust. In some places, it looks like the sediment's completely scraped off of the downgoing plate. So, what is actually going on down there? I mean, it's anybody's guess at this point, I think. Yeah, I'm not exactly pointing at a specific interpretation. It's more just opening the door back up to all these alternative hypotheses. It'd be
Well,
nice if a geologist could say something.
Sorry to ask too many questions, but I mean, you're
That's
not
fine.
really saying there's not high pore pressure. You're saying it's not so high that we're seeing these really bizarre Poisson's ratio. I mean, it could be as high as you like, and you have a very difficult time seeing it seismically.
Yeah, and the other thing, I'm more saying that like it could exist, but it has to be heterogeneous and it can't be on the scale of the entire subduction zone.
Right.
You know, it. I like pointing this out because it's gigantic range that like you're telling me this high pore fluid pressure in a 4 kilometer thick region that spans this giant volume and it never drains. I just don't. I don't think we see that in exhumed megathrust either.
John, you follow up? Yeah. Someone else? Well, okay. If not, then let's join and thank Michael for a fabulous talk. Really thank him for putting together a super clear, really interesting, thought-provoking talk, and for doing it at 7:30 in the morning, starting
That's fine.
Nova, Alaska. So thank you. Yeah. So great.